Okay, here we are with another one. This is n equals 2. I don't know, it's just a little mistake there, a little typo. Okay, now again, look at this series, this general term, and it's if you ignore the minus 6, it's kind of like n squared over n to the fourth, which is kind of like 1 over n squared for very large n. So we suspect convergence because it's kind of like 1 over n squared, which is a p-series with p equal to 2. So we will make our comparison now. This is the limit comparison test. Form a limit and compare two series. You have to know what one series does. This is my comparing series, and I know that it's convergence, so I'm trying to show convergence with this test right now. You can also use it to show divergence, but not using a convergent series as a comparison tool. So trying to show convergence, I have to use a convergence series to do that. Okay, now I find this limit. Let's see what happens here. This would be n to the fourth minus 6 over n to the fourth. Okay, it's pretty easily seen that that limit is a 1. Which is positive and finite. Okay, which means the conditions of the theorem are met. We have a positive number, it's finite. That means both of the series that we're looking at here in this ratio both do the same thing. In this case, both converge. So we have, if it helps, remember, they're both doing the same thing. They're both converging. Okay, that's all we needed to know. Both converge. Okay, now here's the other series over here. Look at it, and you have to kind of peel away some of this. If you ignore the minus 1, then you have n over n to the 3 halves, which is like 1 over n to the 1 half, which is a p-series with p equal to a half divergent. So I'm going to compare this to that series that I just discovered. This sort of behaves like 1 over n to the half. Just like over in the first example, I compared this to 1 over n squared, which is what it behaves like in the very long run. So that's what we're going to do here. We're going to make that comparison to the divergent series, 1 over n to the 1 half. Okay, pardon my sloppiness here. It's n cubed minus 1. Okay, that comes down to this. Let's see, we'll have square root of n cubed minus 1 over, joining these two together, we'll have n to the 3 halves. Okay, so now we can rewrite that. This is a little bit shaky here. I'm not sure why, but okay. This limit, okay, so this can be rewritten like so. Positive n, we can do that. So we'll have n cubed minus 1, and then you'll have that n cubed underneath there. Okay, now that equals this. Sometimes this doesn't always do what I want it to do. Okay, so I got that, and there's a third power there. Okay, now you can see as n goes to infinity, this term over here heads to 0, and we get a 1 as our result. 1 minus 0. This whole thing heads to 0. Okay, so I got a 1, which is finite. Okay, it's greater than 0 and finite, which is all I needed to know to show that both of these series do the same thing. So I know this is divergent. That means that the original series is also divergent. So to remember that, if you're comparing, you can say both. That's the idea. Both divergent. Okay.